So in the previous session, we were looking at the reflection coefficient. We defined what is a reflection coefficient, and then actually we did a derivation, right, to get the equation of reflection coefficient in terms of the load impedance ZL, right, and the characteristic impedance Z naught. Okay, now so let us consider three variety of cases here, right? So that is the case number one. Say ZL equal to 0. In the sense, no load, uh, load is not there, right? Load impedance is 0. This is called as a situation that is a short circuit. Short circuited load. Okay. All right. So when this is the case, what happens to the sorry, what happens to the rho? That is ZL is equal to 0. So 0 minus Z naught divided by minus 1. Right. So now we already know something about the rho. Generally, we expect rho as magnitude of rho into e to the power into some psi, correct? So this is a notation. Now, if I want minus 1, how do you write this? So not possible. See, anyway, I can see 1, right? So this guy can write as 1 into e to the power j. How much? What should be the psi value so that you get a value of minus 1 over there, because this 1 should become minus 1 now. So something should happen here, right? Which angle gives you, right, e to the j theta equal to minus 1? 180, so I can write a pi, correct? So e to the j. So this implies, for in this case, whenever you have a short circuited load, magnitude of this is equal to 1 and the angle is equal to pi or 180 degrees. Fantastic. Let's go to the case 2. So the second case is I'm going to consider open circuited load. That is, load is infinite. So this is open circuit load, right? Now tell me what you're going to write here. So ZL is infinity. So what happens to the rho? Infinity. My equation is ZL minus Z naught divided by Z naught. So you see, recall mathematics. Mathematics in the maybe in some chapter called limits you might have studied. Whenever you have infinity by infinity, you cannot substitute infinity over there, because right now that's the case. If you okay, then right, can you apply and tell me the answer? No, that is possible if you know, if you are doing some differentiation kind of stuff. Right now, I'm not doing that. So there is a much easier way uh, than that. So just think how about canceling a ZL? Can you take out ZL out of this? So right, this is ZL 1 minus Z naught by, okay. Now you substitute. What happens? ZL cancels, right? In internally you put infinity. So that is equal to 1, right? So that's the answer. So rho becomes equal to 1, right? So this means, right, again, I'm going to compare this with magnitude of rho and e to the power j psi. So tell me what is, right, 360 or 0, right? Easier way. Okay, so that means magnitude of rho is equal to 1 and psi is equal to 0. 0, 2 pi, 4 pi, 6 pi, and so on, right? Okay, that's correct. All right. Now you see any other value, right? So that's a case 3, right? We take normally the ZL is complex, right? So this is RL plus JXL, right? In such case, you will see that you are going to get the various values of magnitude of rho and SI value. Okay, so magnitude of rho, right? Right. As of now, since we are not calculating we are not substituting RL and GL, right? So what is magnitude of rho? It's a real value. It's a real value, and we definitely get the psi value as well, right? Normally 0 less than or equal to psi less than or equal to 2 pi. Any value will come into picture. Okay, so these are the three cases which we want to know. Right now, let us see. We understood what exactly is going to happen here, right, in terms of the rho, right? And let us try to understand what happens with the incident wave and the reflected wave, right? Whenever uh, we have the three cases. Okay, so the first case, we are trying to draw a diagram here. Just this is going to help us in analyzing, right, the topics which are going to come after this. That's we are going to derive the input impedance followed by the standing waves and the standing wave ratio. To understand that, this the rho plays a important role over there. So we need to explore more about the rho. Okay, fine. So let us try to understand that. So let me take. All right, let's consider the, okay, this is the graphs for each of the cases. So once again, I'll go back to the case 1. Okay, it's a diagram now, right? So for in case 1, I know that I have a short circuited load. So short circuited load is represented like this. Okay, so this means I'll write SC here, indicating that this is a short circuit. So ZL equal to 0. All right. Now, let us see. Let me try to draw a wave here. So I'll try to draw as neatly as possible. Let me draw one line at the center. This is my reference line. I'll change the color so that that's not a part of our transmission line. It's just my reference line. Okay, so it's something like a zero axis, horizontal axis. That's all. That's this color. And let me use incident wave. I'm expecting the incident wave to touch at a point. Okay, let me assume that I'm going to touch here. Okay, let's see. The wave starts like this, goes like this, 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 and this. Okay, right. So the green color, right, is incident wave. All right, and I'm going to use the red colored for the reflected. Okay, now you tell me what do you expect, right? Where the reflected wave, where should be the reflected wave start? You see, reflection coefficient, it's -1. In the sense, whatever value you have, it should be negative. It's negative of that. So you see, that's why I have used a reference line here saying that that's the 0 volts here. So assume that this point is a 0. Now you see your input is incident wave is touching below that. So that means my reflected wave I'm expecting to start above this, correct? Equally on the other side. So this is where I'm expecting it to start. From there you can draw, right? And right, so you are understanding, right? That's what is the significance of this wave, right? The what you call as the rho value. It actually tells you where it's going to start. All right, okay, so let me see whether this works. Looks like I can touch there. Yeah, almost. Right, so this is how it's going to look like. Right, so for case 1, where I have zero impedance at the load, right? The incident and reflected wave will show this characteristic. Okay, now let me do one thing. I think I'll just erase this once because I can copy the same thing for my other three cases as well. All right. So let me just copy. Otherwise, it takes some time to draw, right? So let me. So okay. Now this is a. Oh, I didn't copy it. Let me try again. I'll draw another one because we have three cases. All right. Let's go back. What happened? Oh, we lost the red wave. Okay, no problem. I'll draw it again. No, no issues. So we know that it starts from here, goes all the way to here, like this, like this, and like this. Okay, fine. So this is a case one, right? And now let's go to the case two. Now you say, right? What does it mean when we say rho equal to one? Wherever you, right? Same point. No, no. It's on the same point. It's increasing, so it will further increase on the other side. Okay, so that means it is going to come like this. Okay, from the same point. It's going to start, and if it is increasing, now you see this is the point. I'll now I'm able to explain, so I didn't explain the previous one. Okay, that's because I had no reference to talk about. Now you see, whenever phase is not changing, right? Phase does not change means if your waveform is increasing, it keeps on increasing even on the other side. It's still increasing. Okay, but you see here now this was increasing, but my wave decreases because phase is 180. There is a phase shift of 180. So 180 phase shift means you change everything, right? So you need to consider even the direction of travel, and that needs to be reversed. If it is increasing, it should decrease. That's why, all right, I had drawn in the same way, but in this particular graph, I need to change something. That is, it's not SC, it's open circuit. So I cannot write this now, right? There is no line here. It's an open circuit. Okay, right. So now let's say this is open circuit and the ZL equal to infinity. So it means rho is equal to 1. Anyway, other values I know already. Okay, let's go to the third case, right? And in this case, I know that I have some phase, right? It may depending upon what psi value you have, it may increase, it may decrease, or whatever may happen. Okay, so what I do, I'll start from this point, I'll increase, I'll decrease. So it's some random, okay, because it depends upon the value of that. So anyway, right now I'm not able to show any specific response why I'm increasing or decreasing, right? Because you know that, right? It is going to, it depends upon the psi value. What? So what I write, I'll write in, okay, I can show you one impedance itself over here. Okay, so there is a resistor. right? So this is ZL is equal to RL plus JXL. So you have some psi value coming into picture, right? So because of that psi value, we are going to get a shape like this. Okay, so now we'll talk about another case of Z naught, which is being real. I think we have discussed about that. What under what condition this becomes real? Z naught becomes real. Yes, yes, yes. It's a lossless scale, right? So lossless means you don't have, right, a reflected wave, correct? So I'll just write a point here. So if VR, that's a reflected wave, and even the current, reflected current is equal to zero, this means uh, Z naught will be equal to simply Vs e to the power minus of whatever gamma Z divided by this is is become I become simply the supplied or the source current into e to the power minus gamma Z. So it will get cancelled, so you just have a magnitude Vh by magnitude Is. That's why we call that this is going to be a real part. All right, anyway, you know this, so I'll skip, move ahead. Okay, right? So based on whatever concepts we studied so far, we will move further to derive the input impedance. Okay, input impedance, so denoted as Z in. Okay, right. So let me draw the similar diagram we used earlier once again. So this is my transmission line. All right. Let's say there is a ZL present. Okay, and all right. Let me also mark the total length of this. See, we have given a notation for this. That is L, correct? L is the total length. Now, what you are trying to measure is the impedance that we are going to see when I look from the input side, correct? Whenever you look into this, what is the input impedance? What is the impedance that you see? That is input impedance, right? So, right. Uh, Now, previously known concept is that the previously known concept is that we can try to represent the ZL, right? We can try to represent the ZL in terms of Z naught, correct? So let's try to recall that equation which we used to write for ZL. So I'll start from there. We know that. Let me try to write as ZL. Okay, so that is ZL is equal to Z naught into e to the power, right? So just remember what was the equation we wrote. ZL is equal to Z naught into, are you able to recall? Hmm. I'll try to write in terms of, let me say, uh, okay, let me use another method over here. That is, uh, okay, okay. I'll explain something more now, so that makes it easier. Let me take another approach to do the derivation here, which is easier. Okay, so let's not consider this. Okay, so you see, in order to calculate the ZL, right? We consider that what is the voltage that is present across this ZL, right? If you remember, we wrote a equation VL. previous derivation. Okay, and also we wrote a one equation for the current, that is IL. Correct? So VL divided by IL is what we wrote. Correct? So that was the impedance that, right, we can measure at this point, right? So I'm marking that now. So at this point, what you are supposed to connect, you will try to identify that. Okay, now what I do, instead of calculating the impedance at that point, I slightly move to this point, slightly away from, say, right here I measure some distance. What I'm supposed to do here, what is the voltage here? Correct? What is the voltage here? Sorry. uh, if you divide, so no, I'll come back, once again, I'll tell you what it is. Now you see, if you measure this particular voltage and that current, then it is fine. Okay, then what you told is right. But now my point is not the voltage by uh, current at that point. Right now, what wherever I have marked this red color line, right, that point I'm not dividing voltage by current. What I'm trying to do here, I'm trying to measure this total resistance. Okay, that's what I'm trying to do now, right? I will get the equivalent of ZL at this point. Correct? At this particular point, what is the total? It looks like, what is the correct volt? What is the, sorry, what is the resistor that you can see when you look into this? Look at the uh, look towards the ZL from this point. No. There is this part is added, right? You see, you are going to get a different value, right? It's not just ZL. Something will come, some value will come, right? Now you see, you don't consider here, move further away, right? Move further away from the ZL. So you move here and measure something else, you get something else, right? Because this is a bigger value. Like that you move, right? How much I should move? I should move till the beginning, come till here and look in, right? Whatever you get is the Z in. So that's how mathematically I want to do a model mathematical calculation now, right? So this is my approach, right? Whatever I calculated here is for the ZL. That is, I know an equation, I know the equation, that is ZL equation. Okay, but as I move to the beginning, now you see, you see the change I'm going to do now, right? What I calculated earlier was, at this point I had, right, some value. But now if you want to move to this, what you are supposed to do, you need to move how much? What is the distance you are going to move to, towards the Z in, towards the source? Total distance is L. Now you see, once again, one more, we bring the convention as well. Okay, convention is that, as per the convention, this is my positive Z axis, correct? So any distance you move like this, right, is negative for me. So you move by a distance minus L, right? So these all the things you need to consider whenever you write an equation, right, implementing the concept I mentioned earlier, right? So let me try to write one simple equation. If that is very clear, then we can easily solve this issue. Okay, we don't have to go with a longer method, easier method. Okay, so let's try to write okay, Z in. Let's try to write a Z in equation directly. So what is Z in? Now the Z in can be written like the voltage, right? Right, voltage, this is the total voltage, not a incident, not a reflected. Okay, the total voltage that you can measure at, say, Z equal to minus L, are divided by the current, my mistake, divided by the current that you're going to measure at Z equal to minus L, right? Normally write the equation, but replace every Z by minus L. Is that okay? So let me try to write the normal equation which we used to write. So right. So normally I have a Z naught outside. look at the equation of ZL. Okay, I am modifying the equation of ZL now. Right, ZL is equal to Z naught into so the input voltage Vs, gamma L becomes minus gamma L. Yeah, perfect, perfect. Perfect, perfect. I'll make it. Yes. So since you understood that, okay. So shall I write two steps here? Saying that once I put Z as it is, then I say Z equal to minus L and I'll do that. So maybe that's easy for you when you follow. Okay. So tell me the general equation. Vs e to the power gamma Z plus Vr gamma Z. All right. Divided by I actually we wrote one more equation, previous derivation. So that is once again Vs e to the minus e to the power gamma z. So in this case, I have to substitute z is equal to minus L. All right. So that's why now I get this equation. So that is z naught into this is Vs e to the gamma L, right, plus Vr e to the minus gamma L divided by Vs e to the gamma L minus Vr e to the minus gamma L. Are you okay with this? Okay, let me try to take a Vs outside now. So that is Z naught. Both numerator and denominator has Vs that comes out and gets cancelled. Okay, so I have e to the gamma L plus Vr by Vs. What is Vr by Vs? Refer back. If you are not able to recall, I will show you. Vr by Vs. Vr is reflected. Vs is the uh, reflected voltage by incident. It's a rho value, correct? Rho value. So I can write, I'll write rho here, rho into e to the power minus gamma L, right? Divided by e to the gamma L minus rho e to the minus gamma L. Let me know if you have any doubt. It's okay, right? All right. Now you substitute for rho. What is the equation for? Because you see, I want to write everything in terms of ZL, Z naught, correct? So that's my fundamental idea here. So let's substitute. So that is Z naught outside. So e power gamma L. So what I do, I plus what is yes, so ZL minus Z naught by ZL plus Z naught times e to the power minus gamma L whole divided by this is e to the gamma L minus once again ZL minus Z naught divided by ZL plus Z naught into e to the gamma L minus gamma L minus. Okay, now let us try to take the common denominator. Both the numerator as well as denominator will be having ZL plus Z naught as the common denominator, correct? Right. So that means okay, this is equal to Z naught into, yes, ZL plus Z naught into e to the power gamma L plus minus gamma L divided by common denominator, that is ZL plus Z naught. Okay, whole divided by, anyway, it's getting going to get cancelled now, right? Okay, so ZL plus z naught e power minus zl minus z naught, yes, e to the minus gamma all divided by z naught. Okay, right? So this cancels. All right. Now what we can do? Okay, let's try to take the uh, sorry, from both the numerator and denominator. Let's try to club the terms containing ZL together and Z naught together. Okay. So anyway, there is a Z naught outside. I want to do this. So let me take a ZL outside in the numerator. E to the power gamma L plus e to the power minus gamma L. And second one is negative, right? Minus e to the minus. All right. So similarly to the same thing with the denominator. So ZL into so e to the gamma L. It's a minus, right? Now minus e to the minus gamma L. Then gamma L. Okay. Yes, yes, yes. E to the minus gamma L. Okay. Now, looking at e to the power theta plus e to the minus theta, right? What's the substitution we can make? Every term, everywhere I can see e to the theta plus e to the minus theta. Either this term, otherwise I see e to the theta minus e to the minus. So what is a substitution? A very basic mathematics, right? From trigonometry or yes, yes, yes. Can you tell me what you're going to substitute for this and what you're going to substitute for this? It is actually a hyperbolic function. Okay. So when you have a positive term between the e to the theta and e to the minus theta, if you add them, you are going to get a cos hyperbolic of theta. Okay. If you have a subtraction, this is going to be sine hyperbolic of theta. Okay. So this, let's use these two in the above equation. So that means this is equal to. So what happens to the numerator? I still have, okay, I'm calculating Z in. Let me write that. So there is a Z naught outside into, right? So you look at the first term. This is positive. So that has to be cos hyperbolic. ZL cos hyperbolic plus Z naught sine hyperbolic whole divided by ZL sine hyperbolic plus Z naught cos hyperbolic. Okay, so instead of theta, I'm going to write a gamma L over there. Okay, so let's substitute that over here. So this is Z naught into, so first term is ZL, this is cos hyperbolic gamma L plus Z naught into sine hyperbolic of gamma L whole divided by, this is ZL into sine hyperbolic gamma L plus Z naught into cos hyperbolic of gamma L. All right. Now what we can do? Okay, we can bring. I'll try to take a cos hyperbolic outside. Okay. So when I take the cos hyperbolic outside this function, so I have z naught. So cos hyperbolic comes out from numerator as well as denominator, and it will get cancelled. So when that happens, I can write zl plus sine by cos is once again tan. So this is tan hyperbolic of gamma L whole divided by. So here I am dividing by the cos. So that is ZL, correct, gamma L plus Z naught. Okay, now moving ahead. Uh, we can do something like, all right. So let me write it in a different way. Later on, we'll verify the various cases. Okay, we got the equation. Okay, this is the equation for Z in, right? I'll just write in the form which the textbook says, right? So you write the constant first. Tan H you write later. That's all. So it is ZL plus Z naught tan o okay, tan H, my mistake, sorry. So this is tan hyperbolic of gamma L divided by Z naught plus ZL. Yeah, okay, tan H of gamma L. So this is a equation which you can use to calculate the input impedance Zn of a transmission line whose ZL and Z0 are known to you. Okay. We also should know what is the gamma value and what's the L value. What's the length of the line, right? So you see that all the basic parameters we know, we can use it to calculate the Zn. Right. So there are no unknown parameters or there are no complex parameter which you need to calculate first and then substitute here, right? So that's why this is a pretty much valid this thing. All right. Okay. Fine. So that's the equation which we were looking for. Now there is another method that is actually you divide the whole equation by Z naught. Okay, so that's actually another method of calculating this, right? So that is some of the books will follow this, right? That is called as a normalized value of ZL, right? So if I see, if so, this is a note. Okay, this is not valid. Sorry, you don't have to follow this always, right? But just check if somebody says that this is a normalized input impedance, then that means whatever I'm writing. Okay, so normalizing ZL, that means every ZL is divided by Z naught. Okay, normalizing ZL means I'm going to call it as a ZL dash, right, which is equal to normal ZL divided by the Z naught. So what is ZL? It's the impedance that you connected at the end of the load, right? So there is a concept called as normalized ZL, which is ZL by Z naught. So in that case, what happens to the Z in, right? Z in still remains same, right? This is how you do that. So Z naught is there. What happens from every Z, the numerator and denominator, you divide by Z naught, or you try to take Z naught outside. That's all. So no, denominator also Z naught comes out. It will cancel, right? Right. You don't have to do that. So it becomes, see, first term ZL by Z naught is what? ZL dash, right? Correct. Tan H of L divided by 1 plus ZL dash. Yes, yes, okay. Right. So you see, this is also another possible equation, right? Where you say, just remember there is a difference, right? That is whatever you substitute here is normalized. That's all. That value is ZL by Z naught. You can calculate the actual right value of ZL by multiplying that with the Z naught value. Okay, so that's why I wrote it as a note, right? Sometime, right? Maybe in the questions or somewhere you may find the word the normalized load impedance. So it means it is already divided by Z naught. In order to get the actual value, you need to multiply by Z naught. Okay, right? So that's one important point we need to remember. Now let us try to uh, okay, let's try to consider various cases as we considered earlier, right? So this is case number one, right? So I'm going to consider the first case as the short circuited line. So when you see short circuited line, what is the meaning of that? ZL equal to 0. Okay, and what is the voltage at the load? I will give a notation VL. Uh, there is no resistance. So what is the voltage is my question. what is the what is the voltage that you can measure across the load? Are you sure? No, consider this to be something like I have a battery here, right? So let's assume that there is a battery. Okay, so this is a plus terminal, this is a minus terminal. So this is the supply. Okay, it goes all the way there. See here, I usually have a resistance, but I don't have a resistance now because I short circuited this. So now my question is that if I measure a voltage here, what is this voltage? It means I'm measuring the voltage between these 2 points. So assume that I have a resistor here so that maybe I'll avoid your confusion. I have two more resistors here. Now you cannot say that whatever is the voltage, right, that you are supplying is available. Now it's something different, but it's a direct answer. So what is the voltage that you measure between the 2 points AB? So my question is, what is VAB? That's what. What is VB? What is VA? You don't need any of the values here. Directly you can answer. That's why I'm specifically asking what is the value. You have to give me a value like 10, 20, 50, 100, infinity, 0, -2. 0, right? Because, right, there is no potential difference. Same potential. VA equal to VB, correct? So that means VL equal to 0, correct? I can write that directly. So in a short circuited line, the voltage across the load is 0, right, at that point. So okay, anyway, this is straightforward. All right, so now you tell me what should be the Z in value. This implies the Z in equal to how much? You can use the equation to substitute. The ZL becomes equal to 0. Not don't use a normalized one, sorry. Okay, so go back to the regular one. Yes, this equation you use. Z naught into, yeah, correct. So you see that. Correct. So numerator ZL becomes 0, denominator the ZL becomes 0. So those two terms are not, this is not there, this is not there. Correct. So Z naught cancels. So Z naught into, perfect. Yeah. So these equations, special cases, you don't have to remember. But if you remember these conditions at any point, whatever is the question, you can make the modifications as required. Okay, so that means this is Z naught into tan hyperbolic gamma L. Okay, and if at all it comes here, you see, uh, in this also you can actually come to the same point, right? So from the normalizing this thing also you can come, you see ZL dash becomes 0. So Z naught tan, that same thing we will get. All right, okay, fine. So that's the case number 1, right? Let's go to the case 2. This is the open circuited line. Okay, that means, right, what is the ZL? Infinity. And what is the IL? I'm not asking VL because VL varies. That's why. Okay. So previous case, I didn't ask what is IL because IL varies. IL is not equal to IS or something, right? As you know that it's a right something like it's a sum of various components, right? Okay. So that's why I didn't ask what is IL over there. Now for the same reason, I'm not asking what is VL, but I'm asking IL. This is straightforward answer. That's why I'm asking. Current infinity. So I'm asking what is IL, correct? So